Welcome to the Hidden Variables, and today I'm having a very special guest. We have Chad Henshaw with us, and we are going to discuss a little bit about his experience, his research, and his future career path. So, hello, Chad, and thank you for joining us. We would like to discuss a little bit your experience and how you got into physics to begin with. So, if I'm not mistaken, you started as a mechanical engineering
Yeah.
major?
Hey, Bar, thanks for having me. I did start. Um, I I've had actually a very strange educational path. When I was 15, I dropped out of high school, and for various reasons, most of which were personal. But when I was 17, my family moved to Georgia, and I started at a community college, Georgia Perimeter. So when I was there, I decided I wanted to be an engineer because I thought it would be a good way to make money. I really didn't know what I wanted to do with my life. Uh, Also, when I was there, I took a class in astrophysics that was very interesting to me. Um, I became good friends with one of the astrophysics professors there, and he was trying to convince me to become a scientist. I was just like, "There's no money in science. What are you talking about? I'm not doing that shit." And little do I know that years later, here I am trying to do it. So, um, after being at Georgia Perimeter for a couple years, I transferred to Georgia Tech and got my degree in mechanical engineering there. After that, I worked as a design engineer for a couple companies. Did gear motors for a while, and then I did thermal systems, and decided that I really hated engineering because it was like there's some good parts and bad parts, but ultimately it's very very business oriented and sales oriented, and I felt like I was losing all of the interesting knowledge that I gained in engineering school. I was gaining knowledge in things I didn't really care about, like how to effectively extract money from customers, and so I was just like, well, I wonder if I could go back to Georgia Tech and get a physics degree. And they let me back in. So I came back to Georgia Tech, got a second undergraduate degree in physics, and kind of was validated in what I was trying to do because I enjoyed it greatly. Met a lot of really excellent people. Did some really interesting research on gravitational waves and black hole mergers when I was there with Deirdre Shoemaker and her group, and then um, through talking with Dr. Mike Chapman when I was taking his optics lab, he turned me on to the Bobby Jones Fellowship, and I applied for that and received that fellowship, which let me go travel to Scotland for a 1 year master's program that was conducted partly between St Andrews University and University of Harriet Watt um, in Edinburgh. And while I was there, the world descended into chaos, and unfortunately, I had to come home early. But fortunately, I was able to complete my program online. Over summer of 2020, I did a research project with Fabia Biancalana at Harriet Watt on the thermodynamics of the extremal Reisner-Nordstrom black hole, and specifically looking at Bekenstein's entropy law, how that can be modified to solve one of the more classic problems with that law. Um, we come up with some pretty interesting results, I think. Overall, I think the project was very successful. Um, Now I'm back at Georgia Tech doing a PhD, and I've now met more excellent people such as yourself. So overall, it's been a long, strange trip, but it's been fun.
That's amazing. And you touch into a lot of points. So let me start from the beginning. You mentioned you started as a mechanical engineering.
Yeah.
Can you tell me the point and your interest growing up from 15 until you finish your mechanical engineering degree and when you go working, what was physics to you as an engineer or as a person?
Well, I can say that my initial interest in physics is probably entirely due to Sean Carroll. When I was 15 or 16, I had dropped out of high school, so I was doing like homeschool type classes. Um, and when you do that, you kind of have unlimited freedom to choose what you want to study. And I found this online course, or no, it was like a DVD set. It was like the great courses or something, and one of them was entitled "Dark Matter, Dark Energy: The Dark Side of the Universe." And I was just like, that sounds cool. Let's look at that. And it
Yeah.
was a course taught by Sean Carroll on basically on cosmology, and I've been fascinated with some of those ideas ever since. So that was kind of the first thing that turned me on to astrophysics. I mean, I've always been a problem solver, like starting off with Legos as a kid. Like I think that's how I got into engineering. Just like I
Yeah.
want to build stuff. I'm pretty good at that. Yeah.
Yeah, that's amazing. And obviously, you came back and you indeed got your undergrad in physics at Georgia Tech, and then you went to do your master's. So, can you tell us a little bit about the master's you did? What was the program about? And I think it was in Scotland.
Yeah, yeah. Um, the master's degree was in photonics and optoelectronic devices, and it was a joint course offered between University of St Andrews, which is there, so they're both in Scotland. St Andrews is kind of a very famous university. They've been open for almost 700 years now.
Oh, wow.
Yeah, and that was one of the big culture shocks of going over there. It's just like, wow, so this university is older than my country. You know, you guys were around doing cool stuff before America even existed. So, I mean, I had a fantastic time over there. Fortunately, I didn't get as much time as I would have liked to explore the country just because of how intense the program was, and also getting my time cut short because of COVID. But you know, I still had an amazing experience over there. Like I said, it was primarily an optics program, so I had chosen that program partly because I wanted to get the experience of studying abroad and kind of diversifying my education, but also because when I was working with Shoemaker, I took her class on gravity, and as part of that class, we had to do a literature review on some topic that interested us and present about it. And I wanted to do something with Hawking radiation because I had never really understood it. I remember reading Hawking's paper. His like, well, it wasn't even really a paper. It was like a little letter that he wrote. Like, I think if we do this math, then it kind of works. And it was a very small conjecture. And I remember reading that and not understanding it at all. So I decided that I wanted to learn more about Hawking radiation. And in doing so, I discovered that there were some experimentalists who were trying to recreate the conditions of Hawking radiation in labs using optics. And the technique for this was actually developed at St. Andrews. Um, so after learning that, I was even more excited about doing this program and getting into these ideas of analog gravity, of using optical or acoustic analogs to model systems that you would only find in like true astrophysical situations. Because ultimately, the problem with astrophysics is that you just can't get there. Like, you cannot measure certain things, like Hawking radiation. It's just too cold, ultimately, with respect to the background temperature of the universe. So, if we ever wanted to get experimental verification of this idea of Hawking radiation, we would never be able to get it from the real world. Or, maybe a million years in the future when we have amazing technology, we'd be able to figure it out, but it's unrealistic. So it was interesting that there's a possibility of doing that using optical analog. And when I was there at St. Andrews, I had a chance to talk with Friedrich Koenig, who right now runs the Hawking Radiation Lab. And there was a possibility that I was going to do my summer project with him, but due to a variety of circumstances, that didn't end up happening. Um, Primarily because I chose not to, because I ended up meeting Fabio, who has is more of a theorist, and theory is interesting to me. So I ended up doing a project with him. But some of the work being done there at St. Andrews is truly fascinating, and I gained a lot from that program, even if it wasn't what I thought I was going to gain. I was hoping to learn more about like light interaction with matter, kind of from the QED perspective, but it ended up being more practical, like how does a laser work, and then like level two, like how does a laser really work, and there was a lot of interesting opportunities that I had as part of that. Like I took a class called Applications of Quantum Mechanics that was largely about how we can cool atoms and ions down to very low temperatures using lasers. But also, as part of that class, I got to write a literature review, again, of my choosing. And at the time, I was obsessed with foundations of quantum mechanics. So I wrote a literature review about some new work being done at Caltech that calls Bell's theorem into question. So that whole experience, that trip, was just rife with academic opportunity. I tried to take as much out of it as I could.
Yeah, that's amazing. Obviously, traveling to different places and meeting other people is something that's gonna expand your horizon and give you different point of view and perspective. As you were mentioning, although your degree was more experimental or practical,
Yeah,
you took a lot of that knowledge, and I assume you're going to implement that within your future research as a theorist.
I
So
definitely
my
hope to.
question, yeah. So my question to you is, what do you think your future research is going to look like? What interests you? Is that something that relates to the foundation of quantum mechanics? Is that dark matter or dark energy in the universe?
So, as I'm sure you're aware, um, what you end up doing for your PhD thesis is not entirely up to you, and it is somewhat dependent on who is available to work with and what money is available to fund your research and things of that nature. So at this point, um, there's a lot of different research going on at Georgia Tech that I would happy to be part of, and that I would be very excited to be a part of. Um, Specifically, there's some work being done on the next generation of gravitational wave detectors, namely the LISA project, or LISA, that's going up into space, or it's supposed to. We'll see how that actually works out. But
Yeah.
that project, if all successful, will let us look at the universe in such a new way that I suspect it will change the texture of our reality with respect to how we understand, man, so many things: galaxy formation, cosmological history. Um, it'll let us refine our timeline of the Big Bang. It'll let us see back further than we ever have been able to before, if we can truly model the gravitational wave background. So being part of that project would I think be amazing, and I would love to work on it.
Do you just want to explain to the viewers exactly what it is? We are trying to take
Sure.
yeah,
Yeah.
the
Yeah.
laser
So
informator on Earth and just implement that in space over very gigantic, large distances in order to detect supermassive black hole gravitational fluctuation.
right. So right now we have several gravitational wave observatories on Earth: LIGO, Virgo, Geo, all the O's. And the problem with them ultimately is that they can only be so powerful and they can only be so sensitive because they're subjected to many, many sources of noise. And the biggest source of noise, or I should say the most limiting source of noise, is seismic activity. And that limits the frequency range of gravitational waves that you can detect. You can't really get to the super low frequencies. And turns out that, for example, in a black hole merger system or any binary merger system, the frequency of gravitational waves is inversely proportional to the mass of the system. So for supermassive black holes, they have very low frequency gravitational wave radiation. So we're just not able to detect it. But we know that it should happen because we have been able to detect other gravitational wave signals. So we now have this idea of putting one of these giant interferometers up in space, and it is a very scary idea to some because what's going to ultimately happen is we're going to deploy these giant laser mirror apparatus to the Lagrange points in orbit, and we can't get there after they have been deployed. So they have to do this origami-like unfolding mechanism and kind of self-regulate and self-assemble. And if there's anything that goes wrong, we can't really send a mechanic out to go fix it. So I think this project is very ambitious, but it's definitely doable. I mean, mankind is capable of all sorts of incredible things, and I think this is something that we could definitely pull off. And if we do, like I said, I think it will change our texture of reality of the universe because we will have a new lens that lets us see far, far deeper into the history of the universe and also into its structure. Being able to look at supermassive black holes, which are ultimately kind of the nodes of cosmological evolution. All galaxies contain supermassive black holes, unless they've been kicked out by merging with another supermassive black hole. So,
Right.
yeah.
So just to touch on that point, the Lagrange point, which you discussed earlier, are points in which you can set a satellite or an object, and in the reference frame of Earth and the Sun, for example, it wouldn't move.
That's right.
And in addition, supermassive black holes are what govern most of the galaxies, most of the spiral galaxies, and because they are so large and so massive, they have so much gravitational pull that basically in the center of every galaxy you would expect to have a very massive black hole. Do you know the mass proportion to our sun, for example?
Oh, that's an interesting question. I think the total mass of the black hole is something like it's on the order of like 1% of the mass of the galaxy, which may not seem like a lot, but it's a lot. It's a single object that has all this mass. And also, I want to touch on something else you said. It's still not clear to us the order in which galaxies develop as to whether they concatenate out of debris and gas and everything come together and then a supermassive black hole forms, or whether these black holes form from many seed black holes and then they attract all of this gas and dust that then forms into a galaxy. There's kind of a chicken and an egg type situation where we're not 1,000% sure which one comes first in the cosmological history. There's been a great deal of numerical modeling about that, but we don't have direct evidence, and that's one of the things that being able to look at this gravitational wave history might tell us. So it'll give us a much better sense of what's really going on in the early universe.
That sounds very exciting because we already know so much about the history of our universe, and having this piece of the puzzle fitting in would be, as you mentioned, a very special time in human history, I suspect.
Yeah.
So, besides that, Chad, would you like to share more about your master thesis?
Oh, sure. So, for my master's thesis, I wrote. So the idea for this thesis was Fabio's idea originally, and Fabio Biancalana, Harriet Watt, amazing theorist, amazing researcher, actually an optics person originally, and still an optics person, but did some work on comparing black hole physics with soliton physics, and became interested in black holes and gravitational theory. I think from working on that, and also just a very widely studied person, and is very aware of many different things. So he had this conjecture on how to fix Bekenstein's law. So Paul Davies in the 70s wrote a paper about black hole thermodynamics in which he demonstrated that for certain black holes, namely those that are either charged or spinning or both, they can come to this condition called the extremal condition. So if the black hole is charged, then the extremal condition would be when its charge is equal to its mass. If it's spinning, it would be when the magnitude of its spin is equal to its mass, or the Kerr parameter A is like spin per mass. And the extremal condition, the black hole's temperature, its Hawking temperature, goes to zero. However, its entropy does not go to zero. The entropy becomes finite, and that violates the third law of thermodynamics. Having a object with zero temperature and non-zero entropy, and it, at the time of writing this paper, it was just like, well, black hole thermodynamics is an analogy to classical thermodynamics for these weird objects that we don't really understand. So maybe it's okay that they don't go to zero entropy. Like, we don't really know what entropy means for a black hole because it's really just a geometric object. We assign things to it like mass and charge based on how we derive the metric, but we don't know, like, the math just tells you the geometry, and so it's unclear, some of these analogies, how true we should consider their interpretation. Particularly in the modern thinking about statistical mechanics and describing entropy as something like the number of possible microstates of a system. What does that mean for a black hole to have microstates when it's just geometry? So there's all sorts of interesting discussions to have about black hole thermodynamics in that direction. But ultimately, Bekenstein's law relates the entropy of a black hole to its surface area, the surface area of its horizon. And the law in geometric units is area divided by 4. And it's that easy. The problem is the area does not go to zero when the temperature goes to zero. Yeah. So the entropy does not go to zero. And Fabio, based on his past work with black hole topology, proposed that we should change this law to say something like S is equal to chi times A divided by 8. Chi is the Euler characteristic, is a topological invariant. And for black holes, chi equals 2. It's always an integer, this number, and you can calculate it based on the Riemannian geometry of the black hole. if you want to get technical, it uses something called a Gauss-Bonnet integral to calculate the topology. And so you can plug that into, chi equals 2 into our proposed equation, and you recover a divided by 4, which is the original equation. And Fabio's idea was that at the extremal point, chi should go to 0. And he was just like, your job is to show that. Or not show it, because it's science. You never know. And we had some original ideas about what this would mean. I'll show this. I worked on it for quite a while. In doing research on this problem, I found that some other guys had already done something like this, using purely mathematical methods, just topology, like no real physics. They demonstrated that for an extremal black hole geometry, the Euler characteristic should be 0. And I thought that was interesting because it meant that we were on the right track. And they had, in fact, proposed the same form of the modified Bekenstein's law. So at that point, the project kind of changed. It was just like, okay, well, how can we come up with a physical interpretation of their mathematical result? And the idea we had relied on the fact that Reisner-Nordstrom black holes, charged black holes, have 2 event horizons. They have an external horizon and an internal horizon. And the idea at the beginning was somehow when the black hole becomes extremal, these 2 horizons collapse into each other and their entropies cancel out. And that is true, that when the black hole becomes extremal, i.e. when its charge is equal to its mass, the 2 horizons touch and there is only a single horizon. But the problem became how to show that they both had an entropy, first of all, and that somehow their entropies were equal and opposite to each other at the extremal point. So I don't know how technical you want to get in this discussion, but what we ended up doing, what I ended up doing, is demonstrating that the temperature of the internal horizon is always negative, and the temperature of the external horizon is always positive. And when you calculate the chi, the Euler characteristic, you do what is called a Wick rotation, so when you integrate over the time dimension, time becomes inverse temperature. So the entropy, if you include the Euler characteristic, depends on the temperature. And you can then show that because the temperature of the internal horizon is always negative, the entropy of the internal horizon is always negative. And at the extremal point, when the 2 horizons come into thermal equilibrium with each other, you can add their entropies together and you get 0. So that was a physical demonstration of the modified Bekenstein's law that was first introduced by Liberati and Polifrone. Although we didn't know it when we set out to do this project, we kind of discovered that over the course of it. And we showed this for Reisner-Nordstrom, which was our original goal. But then I was just like, I wonder if it works for some other geometries too. So I showed it for hair as well, the spinning case. And kind of, I think what we're going to end up working on next, if we continue with this, is to try to show it for the Karen-Newman metric, which is charge and spin. And I think it should be actually pretty easy to do. I kind of took a small stab at it when I was working on the project, but it looked like it was going to get complicated, and I had to do other things. So, because that was only half of the project. The other half of the project was doing something completely different with Reisner-Nordstrom. But I think the modified Bekenstein's law was the best result that we got out of this.
Yeah, that's amazing. So let me ask you a few quick questions,
Okay.
and feel free to abstain if you don't want to answer that.
Go for it.
So, what's your idea? What's your best interpretation of quantum mechanics?
So you're starting with the hard question. Quantum mechanics is very open to interpretation, and I don't think anyone has it right. Um, I think the most promising theory, just based on consistency, is the many worlds interpretation, because ultimately you come down with a choice in your interpretation. You have to choose to let something go. You either let go realism, like the Copenhagen interpretation, with the collapse of the wave function, just lets go realism, or you let go locality, in the case of the pilot wave theory, Bohm's theory, or you let go something even more fundamental, which is like many worlds, which lets go the concept that we live in one universe. Many worlds implies that the universal wave function has the necessary property of branching whenever a system becomes entangled with its environment. I mean, entangled in a quantum sense of entanglement. And you might get kind of skeptical of something so crazy, but you should also be very skeptical of something that breaks locality or something that breaks reality in terms of the Copenhagen interpretation. So many worlds, I think, is good for that reason. It also kind of takes the simplest picture of quantum mechanics, which is just let's use the Schrodinger equation, and that's it. Like that's how you describe the state of the world. So I like the simplicity of that. I have technical problems with many worlds, but I think conceptually it's the best we have right now, especially considering some of the promising work that's coming out of using that theory with regards to quantum gravity. But I do think that the field is still open to other completely different formulations. James Beck at Caltech, I think, is right now working on a completely new formulation that gets rid of Bell's theorem altogether. So there's definitely still a lot of interesting work to be done. It's something that I wish was studied and worked on a little bit more. But I think that is improving in physics overall these days.
Do you think we will have to change quantum mechanics in order to achieve a gravitational unified theory?
Well, all right. So to be very clear, we don't need to change quantum mechanics. Like everyone agrees that quantum mechanics works. Like the mechanics part of it works, and it works extremely well. Like the highest precision experimental predictions that we've ever been able to make, we can make using quantum mechanics. Our interpretation of what that theory means for the real world, I think, is important towards our discussion of deeper fundamental laws like a combined theory or a unified theory of gravity and the other forces. Because ultimately, we just don't know what space is. We know how to write it. We know how it works. Einstein did a very good job of describing how it interacts with matter and how matter interacts with it. But we don't know how to describe what it is in terms of quantum mechanics, and we know that the world is ultimately quantum mechanical. So, physics tends to teach like classical mechanics backwards into quantum mechanics, but quantum mechanics is the foundation, so we need to start from there ultimately and build everything from it.
That makes sense. And I have another question.
Mm-hmm.
If you were to have a dinner with any physicist from any given time, who would you choose and why?
Interesting. Man, just one?
just one.
Man, I'm going to give you a couple that I've thought about, but I've ultimately dismissed. One is Mach. Mach had some very interesting ideas. He was very dogmatic about his ideas, so I think it'd be fun to argue with him. But also, I mean, Einstein would be a pleasure to talk to. It would be really fascinating to see his reaction to modern theories about gravity and quantum mechanics. But I think the person I would most like to meet is Bohr, because man, I think he was just so damn wrong about so many things. But like everyone who ever talks to him talks as if he was like the next Jesus, and his charisma must have been off the charts.
Yes.
So I would it'd be fascinating to talk to him and like experience whatever all those other physicists got out of him. I don't know.
This kind of, I know, this kind of fear of incapability of, winning an argument with him, that would be
Yeah,
quite
yeah.
interesting.
I
Just,
mean,
just
I
off the
mean,
chart.
like when Hugh Everett wrote his PhD thesis on many worlds, his advisor Wheeler was a student of Bohr's, and like there's a list of or there's a series of letters back and forth between them where Wheeler's like trying to assure Bohr that like this theory doesn't like ruin his stuff, and it's like they worship the guy so hard. And I'm just
Yeah.
curious like what it was about him that provoked or that provoked such worship. Yeah, so I'd love to have dinner with him.
That's great.
Plus he's
And
Danish, my family is Danish, so maybe there'd be an interesting conversation there.
there you go. Maybe invite him to dinner sometime. But besides that, Chad, I really appreciate your time, and I wish you all the best and all the luck in your academic future and in your PhD program. It was a pleasure hearing from you today, and hopefully we could touch base in a couple more years when you have more interesting results to share with us.
Absolutely. Thanks, Bar.
Okay, take it easy. Bye bye.
Bye now.